Okay, so I just want to finish then with pointing out a couple of kind of interesting things. One of them is something I noticed about this category of functions, which I think is a really very sort of interesting observation because it it's a sort of observation of a symmetry which um, can has sort of ramifications in all different types of situations. So the observation is pretty simple. It's just what does an arrow from an object f to an object g look like in this category of functions? Well, f is going to be a function from a set A to a set B, and g is going to be a function from a set C to a set D. Now, of course, in this category of functions, f and g are just objects. But then an arrow from f to g is really a sort of pair, a function I from A to C and a function j from B to D, such that this square commutes. So G after I equals J after F. But here's the interesting observation. Whenever we have such an arrow, I comma J, from F comma G, we could equivalently consider that in a different kind of way. We could instead say, well, the same information basically describes a different kind of arrow between different kind of objects. So we could instead think of I as an object, this function from A to C, and J as an object, this function from B to D. So I and J can be thought of as two different kind of objects in this category of functions. And then F comma G is describing this kind of arrow in this category of functions from this object I to this object J. And we see exactly the same setup also gives us this commuting square. So we could instead think of F comma G as this kind of arrow from I to J. So basically, whenever we have an arrow in this category of functions, there's this kind of way to flip it round and think about that kind of arrow, that kind of function pair um, involved in describing the arrow as actually a pair of objects, and then the kind of functions which are being moved by that original arrow then become the kind of descriptions of the new kind of flipped arrow. So we have this way of kind of flipping things, and it's very, very interesting to look at different sorts of substructures of this category of functions. For example, we have functions which correspond to bouquets where we only have vertices. We have these kind of bouquets where everything points. We have these kind of bouquets which encode monomorphisms, which I think actually just correspond to decidable objects. But anyway, I digress. We have sort of these like endo functions, these kind of things that happen in the category of dynamical systems can be considered to be kind of special cases of some of the objects in this category of functions. And in all of these different scenarios, we can think about what this kind of arrow flipping idea means, and it sheds a lot of light on the category. Now, I'll finish with something which is not really finished yet, um, but it's something that I was thinking about a while ago. So here's the basic idea. We have this category of functions. So, for example, we might have a function from set A to set B called f, and a function g from set B to set C. Now we can visualize this function g here like this as a bouquet. But here's the sort of question I'm interested in. If we have these kind of things, how can we extract out all the kind of functional aspects of these objects? How can we go from such a bouquet, and within the category, how can we actually pull out enough information to be able to do things like create this kind of a description? Because this is also a sort of description of this function g here. It's just that I took this bouquet g here, and I sort of then made one object which just involved the kind of loops of this, and made another object which involved the vertices of it. And then there's these kind of arrows which are basically mapping the first loops to the second set of loops in a similar way to the way that the loops are actually connected in this diagram G here. So the question is, how do we do this? And it turns out that the thing, well, at least the thing I found most difficult is if we have a sort of bouquet like this, how can we form another bouquet which just has the same number of loops as G does, but all of those loops are kind of isolated and there's no vertices, well, there's no lone vertices in this other object. So in other words, how can we just form an object which just has 3 loops in this case, and so on? Because that's the kind of thing we want to do in order to be able to kind of separate out this information so that we can kind of represent what's going on here with like separate objects with maps in this category of functions between them. And the other part of this kind of endeavor is quite a bit easier, which is how can we just get these sort of vertices on their own. So if you remember the truth value object in this category of functions, it has a sort of true loop. It also has this other loop and this false loop. Well, it turns out that if we just map everything in our object to this kind of other loop here, this one that's neither true nor false, this kind of dotted one, and then we just find what's the kind of sub-object of G classified by such an arrow, then that sub-object will just be the sub-object which just holds the vertices and doesn't hold any of the kind of loops. So that gives us a way to kind of strip the loops off any particular object. And then in fact, if we have any kind of object which only contains vertices, then we can add a loop onto every vertex just by raising that object to the power of a single vertex, okay, using exponential objects. So there are various ways one can alter things, but like I say, the real problem I'm interested in at the moment is this kind of loop extraction problem. So there we have it. So yeah, thanks for your attention. I hope these kind of things will be useful to you, this kind of repository of information about sets to the power of C. And I kind of urge you to encode these kind of things in computer programs so that we can really like crystallize this knowledge of topos theory.